Hi, this is the first AP Physics C FRQ on the extra credit questions. So we're given a system with a few blocks and a pulley. So we're going to need to know our physics facts. We're going to need to know force of friction equals mu Fn. And we're also going to need to know how to attack two body problems. Draw one free body diagram per object, and then write F net equals ma for each object separately. And that one rope equals one tension. So let's get into it. Let's draw our FBDs for each block separately. So for M2, bottom block, we have our weight force, which is M1 plus M2, because M1's on top of it, times G. Our normal force. The rope's attached to M2, so tension force acts on that. And then the friction force. For M1, we have our normal force. Weight force is just M1G. And then we only have frictional force, no tension force. And then for the hanging block, nothing in the X direction, just in the Y direction. And we have force of tension, and then weight force, which is mg. Let's reset. Okay. The normal force N1 exerted on block 1 by block 2 would just be equal to the weight force. So it would be M1G. There you go. Frictional force F1 exerted on block 1 by block 2. Well, where it's given that our normal force is M1G, we know that our frictional force is coefficient of friction times normal force. So our frictional force is going to be our normal force times, and then our coefficient of static friction between the blocks. And that's just going to be mu S1. Okay. The force T exerted on block 2 by the string. Well, we know since the objects are at rest that our force of tension is going to have to equal our frictional force. Well, our frictional force is going to be equal to the weight force. Sorry, the normal force, and the normal force equals the weight force because it's in equilibrium, times our coefficient of static friction between block 2 and the table. So that's mu S2. And the normal force, we just figure that out. It's going to be the same as the weight. Same as the weight force. And then, if we scroll down, our frictional force is same as our tension force. So that's just going to be force of friction, mu S. Times G. Okay, now we can get into the fun stuff. Suppose M is large enough that the hanging block descends when the blocks are released, so they're not at rest anymore. That's very important. It's a big development. So, if they're not determine the magnitude. Oh, I'm sorry. Determine the largest value of M for which the blocks can remain at rest. Okay, well, with block M, we have weight force, and then we have tension force. And one rope, one tension. And then if we treat both blocks as one, M1 plus M2, and then we have our force of tension and our frictional force. So this is asking, what is the largest value of M? So our tension force can not be greater than the frictional force. So not be greater is the same as less than or equal to our frictional force. Well, that just means our tension force is mg, and then it has to be less than or equal to our frictional force, which is mu S2 times m1 plus m2 times g, and then our g's can cancel out. Actually, I'll erase them to be fancy. And we find that m must be less than, or the greatest m can be, and the blocks remain at rest, is mu S2 times m1 plus m2. Okay? Yes, keep this. Okay. Now it says, now suppose m is large enough. M is large enough that the hanging block descends when the blocks are released. Assume blocks 1 and 2 are moving as a unit with no slippage. So we treat them as one. Okay, determine magnitude A of their acceleration. Well, we need to use Newton's second law. And Newton's second law from our physics fact, we know F net equals ma. Well, what's our net force? Great question. Our net force is going to be weight force of the hanging block minus our frictional force, which is mu, and now it's K2 since it's moving, mu K2 times m1 plus m2 times g. Okay, and then that equals the masses of the entire system added up times acceleration. So to solve for acceleration, we're going to divide by m1, by m1 plus m2 plus m. Over m, and that's our acceleration of the units. Okay? Well, now there's a little development. So it's pretty unlikely there would be no slippage because tension is just acting on the bottom block and it's not acting on the same blocks, on each block. So we need to now calculate the assuming there is slippage, we need to calculate the different accelerations of the blocks. Well, for block 2, block 1 first. Block 1, the only thing acting on it is our frictional force. So frictional force equals m1 times a1 for block 1, because our sum of forces is just frictional force. So a1 equals our frictional force over m1. Well, our frictional force on m1 on block 1, if you recall, was m1g times, and now since it's moving, it's going to be times mu k1 over m1, and then that's going to cancel, And it's just going to be G times mu K1. Times mu K1. Okay, now let's find magnitude A2 of the acceleration on block 2. So this is a little more tricky with our sum of forces, or net force, whatever you want to call it. So sum of forces, again, stuff that makes it go minus stuff holding it back. Well, our sum of forces is going to be our tension force minus frictional force, which here it's going to be mu K2 times G, and then minus the frictional force acting upon 1. Because that's our sum of forces. So now now let's plug in our, and then this equals M2 A2. Okay, well, let's erase up here. And let's plug in our frictional force for our frictional force. So force tension minus mu K2 times minus mu K1 minus mu K1 times M1 times G A2. Okay, so that means our A2 is just equal to this whole thing divided by M2. And that is going to be the magnitude of acceleration of block 2. And that's the final question. So thank you, and I'll see you in the next one. Bye-bye.